Okay, so the next talk, last talk of the morning, is by Liang Tang on fooling polytopes.
All right, thanks. I'd like to thank the organizers for the opportunity to speak. This is joint work with Ryan O'Donnell at CMU and Rocco, who's in the audience. So we'll be concerned with the basic object in this talk, polytopes over the discrete hypercube 0, 1 to the n. So these are functions f that can be described as the intersections of half spaces. F, which are the end of h1 to hm, and each hi is a half space, the sign of a linear form. And we'll be concerned with polytopes over the discrete cube 0, 1 to the n. So these objects come up all the time within computer science. They show up all the time in optimization. The number of half spaces, number of facets correspond exactly to the number of constraints in a 0-1 integer program. They show up in complexity theory and learning theory. And as we know, they've been studied beyond computer science, in combinatorics, in high-dimensional geometry, and so on and so forth. So in this talk, we'll keep things very simple. There's just one complexity measure we'll be concerned with, perhaps the most natural one, the number of facets. So in other words, it's the number of half spaces if you write it as the end of m half spaces. I'll reserve m to denote this quantity throughout. It's not too hard to see since we're working over the discrete cube. M is a number between 1 and 2 to the n, and we would like to get as good a dependence on m as possible. In this talk, for concreteness, we can think of m as poly n, say n to the 10th. So we're concerned with n-dimensional polytopes with poly n many facets. Okay, there are many questions we can ask about polytopes. We'll focus on just one of them in this talk, that of constructing discrepancy sets for polytopes. So what's a discrepancy set? We want a small set of points, the smaller the better, with the following very special property. So here's my set of points. For every m-facet polytope f, f has some true density with respect to the cube. F accepts a delta fraction of inputs in 0, 1 to the n. I'd like it to be the case that for every such f, if its density is delta, if its true density is delta, the fraction of my red dots that f accepts is roughly delta as well. So it's a small set of points that approximately preserves the volume of every polytope in 0, 1 to the n. So a quick observation here is that this is a problem. The name of the game here is explicit constructions. A small random set of points works great. The name of the game here is to construct a small explicit set. Okay, as many of us who have recognized, this is exactly the problem of constructing pseudorandom generators for m-facet polytopes. So what I'm actually going to do is to restate the question in a slightly different language, but it's going to be completely equivalent. So just to recall the standard definition, an epsilon PRG for class C is a function, explicit function, stretching all random bits to many, many more bits, such that no function in your class can tell the difference. So if you feed a truly uniform string to f in your class, its acceptance probability is roughly the same as if you fed the output of your generator to your class within some error epsilon. And we have designed pseudorandom generators for all sorts of classes. In this talk, we'll focus on the class of m-facet polytopes. So here, the dependence, the seed length will be a function of n, the dimension, m, the number of facets, which we can think of as n squared, n to the 10th, and epsilon, the error, which we can think of as 0.1. And up to an exponential, the number of random bits is precisely the size of your discrepancy set. It's not too hard to see that the image of a PRG is precisely a discrepancy set. Okay, so here's our main result. We give an epsilon PRG for the class of m-facet polytopes over n dimensions with seed length poly log m, poly in 1 over epsilon multiplied by log n. There's actually been quite a bit of work on this problem in various special cases, and I'll go into detail in the next slide. But for this general version of the problem, the previous best seed length had linear dependence on m. So the key here is the exponential improvement in m. So in other words, recalling this equivalent view, we give an explicit construction of a discrepancy set of size n to the poly log m, whereas the previous best construction had size n to the m. So there are only 2 to the n points. So a trivial bound is 2 to the n. So this bound becomes trivial when m is roughly n. Whereas for any m being any poly n, our size is still quasi-poly in n. And this is fixing epsilon to be 0.1. Okay, so that's our main result.
And if you take a random set, how big does it be?
Great. The random set is log n plus log m plus log 1 over epsilon. So we are within polynomial, our log n dependence is optimal. We are within polynomial of optimal for log m, but we are exponentially off in 1 over epsilon. Yeah. You preempted my next slide. Okay, so good. Let me talk more about previous work here. So there's been quite a bit of work on this. Let's focus on the dependence on m, the number of facets. So recall that a polytope is the intersection or the end of m half spaces. So the work of Gopalan and al. Gave a PRG for a much richer class of functions, any function, not just the end, of M general half spaces. However, that seed length had a linear dependence on M. And it's not too hard to see that given how rich this class is, it certainly contains every function of M variables, because a single variable is clearly a half space. You cannot hope to get seed length better than linear in M. However, if all you cared about was the intersections of M general half spaces, you could hope to do better. So then came a pair of works focusing on the intersection of M half spaces, and indeed they got this exponential win in seed length but under certain technical conditions on half spaces. So the first work was the intersections of M regular half spaces, the work of Harsha, Cliverts, and Meka. This is going to be a very important paper for us, and this notion of regularity is going to be very important for us, so I'll define it carefully soon. For now, briefly, a regular half space is one for which the weights are very evenly spread out. So assuming that weights are very evenly spread out, they give such a seed length. And then for an incomparable class of half spaces, Rocco and I gave a similar kind of seed length. This notion is less important for us, so I'm not going to define it. And in this work, we solve the general problem. We give a PRG for the intersection of M general half spaces, not assuming regularity, not assuming low weightness, with a seed length of polylog M. So in this sense, it subsumes these two works, but of course we build quite heavily on the machinery and the ideas in Harsha, Cliverts, and Meka. Okay, so let me just comment a little bit on the other parameters, but I've already said what I want to say on the last slide, which is that the epsilon dependence is still exponentially off. So a very nice open problem, which I'll cycle back, is to get polylogarithmic dependence on 1 over epsilon. And even for these special cases, as you can see, our dependence is poly in 1 over epsilon. Okay, so before diving in, let me actually zoom out and say that this fits into a line of work on these PRGs for geometric objects. So you can ask the same questions about just a single half space. And by now we have a fairly good understanding of the seed length required to fool a single half space. In this work, we are exploring one generalization where we are not dealing with just one half space, but the n of m many half spaces. There's a different line of work which I will not touch on, but it's a beautiful line of work exploring a different kind of generalization. It's still a single function, but rather than a sign of a linear form, you look at a sign of a degree d form. Okay, but we'll focus on this branch. Okay, so this is a structure of my talk. There are two parts. The first part has nothing to do with our work. Well, it's not our work. The first part, I'd like to tell you about beautiful connection between this problem and central limit theorems. It's a very versatile and powerful framework for designing pseudorandom generators from central limit theorems introduced by Meka-Zuckerman and Harsha, Cliverts, and Meka. And we'll see that it's especially effective for analyzing this class of regular half spaces. And in fact, one of the main points I hope to get across in the first part of the talk is that central limit theorems and this notion of regularity really go hand in hand. Okay, then that'll bring me to our work, which is moving beyond regularity. And I'll outline some of the challenges in dealing with general half spaces that are not necessarily regular. We'll use this framework, but it requires us to bring in new ideas and new ingredients. One of which unfortunately I don't think I have time for, which I hope is independently interesting, is a new high-dimensional Littlewood-offord anticoncentration inequality, a new Littlewood-offord theorem for polytopes. But I'm happy to talk about this offline or at the end of the talk. But so for the first part, in fact, for the main part of the talk, I'm just going to focus on telling you about this very nice connection between this class of problems and central limit theorems. So just to briefly recall, right, so this is the first part, and I'm going to focus on the example of fooling just a single regular half space. And we'll see in just 2 slides, finally, what this definition of regularity is. Okay, just to quickly recall, central limit theorems say that the sum of many nice, reasonable random variables, for us, this will be the notion of regularity, converges to a Gaussian of the same mean as variance as the sum. Each xi itself may not look like a Gaussian, but if you sum many of them, they start to look like a Gaussian. There are many notions of convergence. In this talk, we'll focus on convergence in CDF distance, or Kolmogorov distance. Just a weight that S places under any threshold is roughly the same as the weight that a Gaussian places under any threshold. As we'll see, this notion of convergence syncs up perfectly with that of a half space. A half space outputs 1 if and only if the linear form evaluates to a value less than theta. So this is really like the right notion to look at when you deal with half spaces. Okay, so let's look at explicit central limit theorem. The Berry-Esséen central limit theorem is a sort of a quantitative central limit theorem. So given an epsilon regular linear form, This is one, a linear form in which no weight is too dominant. Every weight's magnitude is at most an epsilon fraction of the overall 2 norm. This is what a regular linear form means. A good example to keep in mind is probably when all the weights are the same. Just think of all wi's are 1. In fact, in this talk, when I say regular, maybe just have in mind that example of like majority, when all the weights are 1. That's the most regular half space. Epsilon there is 1 over root n. So given such a nice linear form where all the weights are spread out, if you pump in bits as inputs, the sum looks like a Gaussian. It's epsilon close to a Gaussian in CDF distance. So I guess epsilon here bounds this like height of this little error triangle here. Okay, so that's the central limit theorem. Let me just make one obvious but crucial remark, which is this notion of regularity is crucial for us. It's somewhat a very simple and somewhat silly example, but consider S of x equals x1. This is a very non-regular linear form. It's sort of the opposite of a majority. Here x1, w1 is 1, epsilon is 1, so it's the worst in terms of regularity. And indeed, the CDF of a bit looks nothing like a Gaussian. You need things to be spread out for the central limit theorem to kick in. And we'll revisit this observation in our work. But now assume we're dealing with regular linear forms. Okay, so I've told you about central limit theorems, but what does that have to do with the problem we are interested in, which is fooling linear forms, fooling sign of linear forms? Well, suppose you're given an epsilon regular, just a fully regular linear form, S of x. The CLT says that you converge to a Gaussian in CDF distance, meaning S of x, where x is uniform, the probability is roughly the same as the mass is roughly the same as what a Gaussian places under theta. That's what a CLT says. What does it mean to fool the linear form sine of S of x minus theta? It means to cook up a pseudorandom variable such that the weight that S of x, where x is uniform, places under theta is roughly the same as what would happen if you fed it pseudorandom bits instead of truly random bits. That's what it means to fool the half space sine of S of x minus theta. So the left-hand sides are the same. In one case, you're comparing it with a Gaussian. In the other case, you're comparing it with a pseudorandom variable. So given this, it sort of suggests that it would be very nice to have a pseudo-random version of the Berry-Esséen central limit theorem. If you had that, you could apply the triangle inequality and get this. So this is the observation that a beautiful paper on Meka and Zuckerman made, and they carry out this game plan. They wanted to design pseudo-random generators for regular half spaces. They observed that the Berry-Esséen central limit theorem tells you that S of x converges in CDF distance to a Gaussian. They de-randomized the Berry-Esséen central limit theorem. They cooked up a suitable pseudo-random y, which I'll tell you about on the next slide, such that even if you fed S, the pseudo-random y, it still converges in CDF distance to a Gaussian. Given this picture, using the Gaussian as the middle person, they've shown that S of x and S of y are close in CDF distance. And that's exactly what it means to fool sine of S of x minus theta for every theta. So this is how they got a PRG. Really nice. Okay, so let me tell you a little bit about the generator, the structure of the generator. They have n variables. We want to use a randomness efficient way of feeding values to them. They hash it into 1 over epsilon squared in many buckets. The quantitative parameters are perhaps not super important for this talk. They hash it into 1 over epsilon squared in many buckets. Because there are so few buckets, they can afford to do this independently across buckets. Independently across buckets, they assign the variables that fall in that bucket according to constant-wise independent distribution. This is the generator. And what they were able to prove was that even if you assigned y1 to yn this way, if you sum them up in a regular way, the sum converges to a Gaussian, like what you expect if you assign them fully randomly. And by the triangle inequality, it shows that this distribution fools regular half spaces. And it's not so hard to see that the C length you get, there are only 1 over epsilon squared in many buckets. And to generate a constant-wise independent distribution, you need C length roughly log n. So this, using log n over epsilon squared many random bits, I can assign values to n variables, such that when you sum them, it looks like a Gaussian. I should say before moving on that they do a lot more in this paper. It's a really, really nice paper, but this part is what's going to be most relevant for us. In this talk, in fact, all PRGs, you can think of them as having this structure. Hashed n variables in a certain number of buckets. The number of buckets may need to be larger. and assign values independently across buckets according to a k-wise independent distribution for some k. So we may have to ramp up the parameters, but it has this general structure. And the analyses get more and more complicated. Just one sentence about this. Roughly speaking, they reduce to showing that each bucket is a mega variable, and they apply Berry-Esséen to 1 over epsilon squared many independent mega variables. Yeah, very nice. Okay, so that's how to fool a single regular half space. You can think, okay, now I'd like to fool the intersections of m many regular half spaces, where think of m as n squared. We'll see it's the same overall framework, but they have many cool new conceptual and technical new ideas and ingredients. I'm just going to have time to highlight, in fact, just one. Okay, so we are given a polytope where every facet is regular. So recall that the key technology underlying the Meka-Zuckerman paper for a single regular half space was the central limit theorem. If you sum many real-valued random variables, none of them are too dominant. It's a regular sum. It starts to look like a Gaussian. Now we're dealing with m many regular half spaces. So we'll need an m-dimensional central limit theorem. If you sum n many rm-valued random variables, m here, the dimension of the vectors correspond exactly to the number of half spaces you have. If you sum many of these vectored value random variables, none of them are too dominant in a sense that can be made precise, then it converges to a m-dimensional Gaussian and CDF distance. And again here, there are many notions of convergence. The one that they use and the one that's relevant for this problem is that of multidimensional CDF distance. And just as how CDF distance in one dimension exactly captures the acceptance probability of a single half space, multidimensional CDF distance exactly captures the acceptance probability of an n of m half spaces. So there's really the right notion of closeness to look at for our problem.
So then why do they get on intersection and not an arbitrary function of...
CDF distance is just one orthant. For arbitrary functions, you need 2 to the m orthants. Yeah, good question. And in fact, let's talk about this offline. You can get an arbitrary function, but you have to pay m in C length. Yeah. Okay, good. So they proved this. This has nothing to do with de-randomization. They proved this very nice central limit theorem. And they follow the same game plan. Now, instead of one regular half space, I have m regular half spaces. I'm going to arrange them in a matrix Rm by n, where every row of A is regular. Every row is the weight of a regular half space. They proved the multidimensional Berry-Esséen theorem, showing that Ax, where x is truly uniform, converges to an m-dimensional Gaussian. They didn't just prove this central limit theorem, they also de-randomized it. They showed that under a pseudorandom y, Ay is also CDF close to the same m-dimensional Gaussian. So they converge to the same Gaussian. And using this Gaussian as a middle person, you can say that Ax and Ay are CDF close by the triangle inequality. And that's exactly what it means to fool the intersection of half spaces specified by A. And what's y? Y is exactly the Meka-Zuckerman generator with different parameters. Hash the variables into certain number of buckets, independently across buckets, assign it to k-wise independence for some k. And they show that under this distribution, Ay starts to look like an m-dimensional Gaussian too. Okay, great. So this is a really nice, powerful, versatile framework established in these two works. Hopefully, though, we have seen that notion of regularity is very crucial to this framework, even in the one-dimensional case. So in my remaining time, let me talk about intersections of general half spaces. So as alluded to, the main challenge, even in a one-dimensional case, is that the central limit theorem simply does not hold when you're dealing with non-regular half spaces. If you have a sum, if the wi's that are dominant, it's just not going to look like a Gaussian. And recall this, the simple, somewhat silly, but example s of x equals x1. x1 is very dominant. A bit, the CDF does not look like that of any Gaussian. So this notion of regularity is really crucial to the central limit theorem, and hence also very crucial for the PRGs that are designed based on the central limit theorem. So the key challenge in this work is to bypass this Gaussian middle person, not because we're trying to be smart or trying to have better parameters, just by necessity. So our setup is that we have m general LTFs, the weights of a general half space not necessarily regular, that's A. Ax is not going to be close to a multidimensional Gaussian. If it's not going to be close under uniform, it's not going to be close under pseudorandom. And yet, our goal of that of fooling the intersection of half spaces defined by A is exactly that of showing, cooking up a pseudorandom Y such that AX and AY are close in CDF distance. So sort of the conceptual challenge we had to overcome in this work is sort of step out of this framework of essential limit theorems. We'll still be using, so sort of bypassing the Gaussian middle person. Okay, however, even though, so this is our result, we'll cook up a pseudorandom Y such that AX and AY are CDF close, regardless of what A is, just an arbitrary A. We will not go through the Gaussian because we cannot. However, we'll still employ central limit theorem-based ideas. In particular, we'll use the Lindenberg replacement method, sort of very powerful and versatile technique for proving central limit theorems. It's basically equivalent to the hybrid method in computer science. We'll see that. And this is Meka-Zuckerman and Harsher-Cliven's Meka's strategy for the all-regular case. And however, since regularity is crucial for the truth of the statement, is crucial for the technique, we need new ideas and ingredients, two of which are pseudorandom generators for CNF formulas. It is a very, very well-studied class of formulas in pseudorandomness. And as I alluded to, also a new high-dimensional Littlewood-offord theorem for polytopes. I'm not sure if I'll have time to speak about that, but I hope I do. Okay, so this is a structure for the rest of the talk, and it's also the outline of our proof. First, I'll start with a useful decomposition for polytopes, relating general polytopes with this notion of regularity that I alluded to. Given this decomposition, I'd like to talk about a smooth version of the problem. For that, I have to explain why the current version is not smooth. And I'll tell you about the smooth version of this problem. I'll talk about proving the smooth version, which is really the main part, and what I may or may not have time to go into, and this is what involves the Littlewood-offord anticoncentration inequality, is how to go from this smooth proxy of the problem back to the actual problem. Okay, so let me start with this useful decomposition of polytopes. Again, I'd like to try to relate a general half space with a regular half space, a general polytope with a regular polytope. So what's a regular half space? It's a half space for which the weights are spread out. No weight is too dominant. A half space does not have to look like this. The weights of the general half space could look like this. This is just a single half space. But not a very difficult argument. One can show, in fact, that every half space, every arbitrary half space can be made regular by just fixing a few coordinates. Think of this as literally a constant, like 10 for this talk. You can make every half space regular by fixing a very small number of coordinates. This is not precisely true. There's a different case, but in some sense, this is even better for us. So for this talk, maybe just pretend that every half space can be made regular by fixing a small number of coordinates. Okay, so here's the regularity lemma in a picture. If you give me any half space, I sort the weights according to its magnitude. Then there's a small number of head variables, 1 over epsilon squared. And again, for this talk, just think of it as 10. After which, the remaining n minus 10 variables will be very well spread out. So this is a structure theorem for any half space. We're not dealing with a single half space. We're dealing with m many half spaces. But we can, of course, apply the structure theorem to each of the m many half spaces in our polytope. Yeah, so one remark, and again, for each of them, think of it as literally 10 or 3. One quick remark I'd like to make is that each of the heads are small. Each of the heads have size at most 10. However, we are dealing with m many half spaces, which is more than n, say n squared. So the union of all m heads could cover all of n. So there's a naive strategy here, which is to sort of like restrict away all the head variables. That's not going to work when you're dealing with more than n half spaces. You cannot, if you restrict away all the heads, you may be left with nothing. The first half space may have the head being x1, second half space may have the head being x2, and so on and so forth. So that's not what we're going to do, but yet this picture is still going to be useful for us. We're not going to reduce to the regular case. Okay, so this is our setup. This is what we have to solve. We are given an intersection of m arbitrary half spaces. And we're going to look at the weights as a matrix, R m by n matrix. Every row of the matrix, we can highlight a few variables that are large, such that for that row, if you ignore the large variables, what you're left with is a regular linear form. However, the union of all heads could still cover all n coordinates. And our goal is exactly to show that given any such matrix, any matrix, to cook up a pseudorandom y such AX and AY are close in CDF distance. And this mental picture will be useful for us. And what's our y? It's again the Meka-Zuckerman, Harsher-Cliven's Meka generator with different parameters. The key is to prove that under such pseudorandom distributions, we're still good. Okay, so that's the decomposition of polytopes. Next, I'd like to tell you about a smooth version of the problem, which intuitively, on a technical level, is easier to deal with. So in what sense is the current version not smooth? I'd like to show that AX and AY are CDF close. What does it mean to be CDF close? It means that for every orthant, well, I guess translated orthant defined by B, so this is an orthant, the probability that AX falls in this orthant is roughly the same as the probability that AY falls in that orthant. This is exactly what it means to be CDF close. I'll just rewrite it. I'm doing nothing here. Just rewriting it as expectation of OB, the orthant indicator of AX close to AY fed into orthant, the OB indicator. And the reason why this problem is not smooth is because OB is a discontinuous function. It's 1 here, it's 0 here, and there's many points of discontinuity on the boundary. This is going to be inconvenient for us, so I'm going to work instead first prove this closeness with respect to not this 0, 1 valued indicator, but like a smooth approximator to it. Now it's a bounded value function, and this is in this line of work is sometimes called a mollifier, and this is completely standard. It appears in HKM, in Meka-Zuckerman, in the proofs of central limit theorems. So let me just say one word about what this smooth approximator is. It's a very standard way of smoothing out a function, adding a little bit of Gaussian noise to the function. So this is a hard function. What does O tilde look like? Well, okay, we add some Gaussian noise. There are going to be two important properties for us. First is that we like O tilde to still look like O. It should be a good approximation to O. And for our purpose, it's the following. There's a small error region, unsurprisingly close to the boundary, such that you can make errors. But if you're far away enough from the boundary, you should be very close to 1, like you should be. And if you're far enough outside, you should be close to 0, like you should be. And this small error region, you can go from 1 to 0. That's the first property. And the second property, a technical property that we'll have and we'll need, is that this smooth function has small derivatives. The precise form of this equation is not too important, but roughly speaking, for every order C, think of C as 3 or 4, the sum of partial C derivatives, sum of magnitudes at most polylog m. So I just want to point out one surprising thing, which is that you're summing m to the C many things, and it comes out to polylog m. And this is crucial in us being able to get polylog m seed length. Okay, so these are the two properties we'll need. And before moving on, let me just remark that these two properties are in tension, right? To get the first one, we'll like this strip to be as small as possible to get a better and better and better approximator. However, intuitively, the smaller and smaller you make your error region, the derivatives are going to get larger and larger and larger. So you have to balance them out. It's good that they're in tension, right? So you have to balance them out carefully. Okay, but now we'll work with O tilde instead of O. Okay, so good, I have time. Let me talk about the main part of the paper, which is just proving the smooth version and how to go from the smooth version to the actual version. So I'll go to the full, not the orthant indicator, but the orthant mollifier. So this smooth function, it cannot tell the difference whether you feed it AX or AY. So what's Y? It's this pseudo-random variable where you hash things into buckets, and every bucket, independently across buckets, you fill it in with R-wise independence. Here's a small observation. Of course, you can view a uniform distribution this way also. It's somewhat silly way of doing it, but of course, you can describe a uniform distribution this way as well. Hash it in the buckets, independently across buckets, use full uniformity within each bucket. But given this picture, a proof sort of suggests itself. You want to use the hybrid argument and to go slowly from the picture on the left to the picture on the right. So this is a bucket-wise hybrid argument, also employed in previous works. I'll start off with a picture on the left, all buckets filled in uniformly, a uniform string. Bucket by bucket, swap out a uniform bucket of bits for R-wise independent bucket of bits, and argue that each swap incurs small error. At the end of the day, I'm just going to union bound over all buckets. So the last technical part of the talk, I'm going to tell you about how we bound the error incurred just in a single swap. Just think about starting off with this and swapping out the first bucket for a bucket of R-wise independent bits. Okay, so fix a bucket of variables. You started off with A, which encoded your weight matrix over all n variables. You can restrict it to the variables in your bucket. So these are the variables that fall within bucket B. Think of it as the first bucket. There are some large variables, and if you ignore the large variables, for every row, there are some large variables, a few of them at most 10. If you ignore the large variables, everything else is very well spread out. And our goal is to show that if you swap out this bucket, a uniform random assignment versus a pseudo-random assignment, it's still close for this bucket. So the first thing I'm going to do is to decompose A to the B, which is A restricted to this bucket B, into H plus T, the head part and the tail part. Yes?
Assume that there is a single one, or where
Sorry?
there is a single one big?
10. Yeah, a small constant number.
But can you get to a situation where you can assume it is 1
No.
or 0?
No. No, it's like 1 over epsilon squared.
Even in each bucket?
Even each bucket. Yeah, we can only use very few buckets. That's why. Yeah, because we are paying independently across buckets. Yeah, so maybe, this picture may be misleading. It's like 1 over epsilon many, and then the bucket size is still roughly n. It's like, order n. Yeah, so it's a big bucket. Yeah. But if you ignore the small number of variables, it's regular. But yeah, it's a constant, but it's not 1. Okay, and I'm going to write A to the B as the head variables plus the tail variables, just a sum, this sort of disjoint sum. So given this, this is just, nothing is happening here. I'm writing A to the B as the head part plus the tail part. And my goal is to show that hx plus tx is close in expectation to hy plus ty with respect to this test function, or this distinguisher, which roughly speaking behaves like an orthant. Yes?
So just to be clear, that H is like the union of all the head variables?
Exactly.
Okay.
Yeah. So every row is sparse, but every column may have a 1. It may cover all of n. Okay, just a quick remark, and here's where we start deviating from central limit theorems and on previous proofs. The head variables, in a central limit theorem, you always assume that you're given either a regular linear form or a tuple of regular linear forms. So there's no head. So everything is a tail, and so every row is regular. And so here's where we start deviating from here's where our challenge comes in. Okay, so our goal is to show that hx plus tx is close to hy plus ty with respect to the distinguisher O tilde. Ht is the tail variables. That's a nice property. All the entries are small and spread out. This may not be true for this may not be true for H, but H also has a nice property. H is going to be sparse. Every row is going to be sparse. So you're looking at the sum of H plus T, where every row of H is sparse, and T is such that every row is very well spread out. And your goal is to show that this function that maps an input z to O tilde of hz plus tz can be fooled. So tz is, the entries are small. So you're looking at, sum of a big thing plus a small thing sort of suggests to use a Taylor expansion to bound the error. And a multidimensional Taylor expansion, the exact expression is not too important, but as we would expect in a Taylor expansion, there's a zeroth order term, there's a first order term, second order term. You truncate it somewhere, you incur some error. Okay, and we like to show that in this Taylor expansion, if you feed in uniform bits for z versus pseudo-random bits for z, the value of this Taylor expansion is small. So naively, we could try to fool every term of the Taylor expansion. So as a warm-up, does it even fool the zeroth order term of the Taylor expansion? Is it true that H, the head matrix, cannot H of x and H of y, Hx and Hy are close with respect to O tilde? And again, this is sort of our main challenge because in previous works, the proof is very much similar, but this was a no-op. This was a free step because H is the constant zero function and trivially, all the work comes in here. But here, even in the zeroth order term, we're starting to see some of the challenges come up when we deal with non-regular linear forms. So let me, in the rest of my talk, let me just talk about this step. Okay, so there's no tail because we're dealing with a zeroth order term. So Z maps to O tilde of Hz, where H is a sparse matrix. And O tilde is a mollifier for the orthant. And H has a nice property that every row of H is sparse. So what's O tilde? O tilde is a approximator to the orthant function. And it's obtained by adding a little bit of Gaussian noise to the 0, 1 value indicator of the orthant. What's an orthant? You fall in an orthant if and only if your first coordinate is at least a certain thing, your second coordinate is at least a certain thing, the third coordinate is at least a certain thing. In particular, you fall in an orthant defined by B if your first coordinate is at most B1, second coordinate is at most B2, and so on and so forth. So it's the product across coordinates, m dimensions of some indicator of whether you fall, whether your threshold is satisfied. And the ith thing in the product depends on the ith row of H across all m. And the ith row of H is sparse. So every function in the product, there are m functions, and m is large, but each function only depends on a few coordinates. So this is the product of Hunter's, the end of Hunter's, and the end of Hunter's is something we know and love. It's a CNF formula, and we're good at fooling CNF formulas. So combining the product structure of O tilde, which really the product structure of O tilde is inherited from the product structure of an orthant, plus the sparsity of our head variables, we can show that to handle just a zeroth order term, it suffices to fool small width CNF formulas. And this is very, very well studied. We have very good PRGs for it. Achieving, in particular, when you're dealing with an M-clause CNF formula, you can achieve polylog M seed length. So in simple, but key idea is that we're dealing with the product of K Hunters, a product is an N, that's a width K CNF. Okay, so taking a step back, our goal is to show that we fool the orthant modifier. We looked at its Taylor expansion. By the way, the reason why we want to work with a smooth function is because we want to take the Taylor expansion. That's why we want to work with a smooth function. So we have the zeroth order term, which we show that is connected to the problem of fooling CNFs. There are intermediate terms. It's more complicated. In the first, the zeroth order term, there's no tail variables. Whereas now you're looking at the interaction between the head variables and the tail variables, and you're looking at derivatives. But the key idea is the same. It's the product structure of, now not the product structure of O tilde, but its derivatives. But if O tilde has a product structure, then so does its derivatives. It's also a product structure. H is sparse, and suffices for a pseudorandom variable to fool CNF formulas. Things are more complicated now because there are tail variables, but the key idea is this. Just a quick remark. We're crucially using the fact that we can fool CNFs to very high accuracy. For, say, the cth order, you're dealing with m to the c many terms. We kind of do a naive union bound. And because we can fool CNFs to such high error, we can afford to do this. So that was key for us. So we fool the intermediate terms. We truncate it at a certain error, and the way we deal with the error is the same as previous work. Perhaps not surprisingly, because we're dealing with the Taylor expansion, we have to control the derivatives. And this was the magical fact I alluded to at some point, which is O tilde is a good approximator to O, and yet it has good derivatives. So for the cth order, error term is some expression depending on the sum of magnitudes of the cth order derivatives, and yet the m to the c many terms come out to polylog m. This is a fact due to, it's due to Bankus. Okay, so what did we just sketch? We're dealing with the soft function, the soft modifier for the indicator function. We showed we were going to proceed by a hybrid argument, and we showed how to bound the error incurred by a single swap. And in fact, that's how we bound the total error. We just take a union bound over all swaps. Okay, that's my cue. Whoa. All right, time to wrap up. 5 minutes, oh great. In that case, let me tell you about going to smooth. Okay, so let me actually show how to go from the smooth version to the actual version. So what we have shown is closeness with respect not to the orthant indicator, but some sort of smooth approximation to the orthant. In particular, this function is correct, very close to correct when you're sufficiently deep inside the orthant. You're correct if you're sufficiently outside the orthant, and then on this orthant boundary, you're making errors. You may be 0.5 when you should be 1. And what we really want to show is closest with respect to this hard threshold. You're just 1 inside and 0 outside. So when are you in trouble? You're in trouble if you have a lot of mass on this boundary. So this is another conceptual difference in what we have to do. In this step, from going from the soft to the soft mollifier to the hard threshold, traditional proofs of central limit theorems, such as Harsher-Cliven's Meka, they relied, since they use the Gaussian as a middle person, this step follows from Gaussian anticoncentration to bound the mass that a Gaussian places on this orthant boundary. And in fact, here there's a very nice theorem of Nazaroff that gives a good bound on this. And this is what Harsher-Cliven's and Meka used to go from smooth to hard. For us, since we're bypassing the Gaussians, we cannot use Gaussian anticoncentration. We have to prove Boolean anticoncentration, which is formally even, at least it's a harder task. In a formal sense, Boolean anticoncentration implies Gaussian anticoncentration, roughly speaking, because every Gaussian is just the sum of many Boolean bits. So let me just tell you about what we need. We have to show that AX, where X is uniform random, doesn't put too much mass on the orthant boundary. So let's forget about that, and let's talk about Littlewood-offord, which I think we all know. So it says the following: let W be a single linear form. The entries are all at least 1, some sort of normalization. Then for all open intervals of radius 2, the probability that W dot X, this linear form, falls in this interval is at most 1 over root n. And in fact, so in pictorially, well, W dot X is a discrete sum, but imagine it looks like this. Any way you slide this interval of width 2, you catch at most 1 over root n of the mass, of the Boolean mass. And in fact, we know exactly what the right answer is, and it's exactly tight when W is the all ones vector. So here's what we needed. It's a high-dimensional generalization of Littlewood-offord. If you specialize everything I'm about to write to m equals 1, you get Littlewood-offord. So now instead of dealing with one linear form, we're dealing with a matrix of m linear forms, normalized to have every entry at least 1. For all orthant boundaries, this is our generalization of an interval, real interval. It's just the orthant defined by B minus the orthant where every coordinate is shifted by 2. Okay? For all orthant boundaries, can we bound the probability that AX falls in this orthant boundary? So it's the union of m dimensions. You can apply Littlewood-offord m times and take a union bound. You get m over root n. But again, we want to think of m as n squared, n to the 10th. This is not a good bound when m is that size. What we are able to show is that we get a good dependence on the dimension. We prove root log m over root n, which allows us to take m being n squared, which we show is tight. So that's the Littlewood-offord inequality we had to prove. Our weight matrix may not satisfy this, so we need various technical extensions to deal with the fact, but this is really the core. We reduce to this assumption. And just a word, we build on and extend techniques from a paper by Daniel Kane, which bounds the average sensitivity of polytopes. This is related, but not exactly the same. It seems like this is slightly, well, we recover his proof as a special case. So, but of course using his ideas and his techniques. Okay, so just a recap of the proof structure. We have a useful decomposition of polytopes relating this notion of regularity with a general arbitrary half space. We talked about a smooth version of the problem, where instead of dealing with like the 0-1 valued indicator, we dealt with a smooth version of it. We talked about how to prove the smooth version using the hybrid argument, and using Boolean anticoncentration, going from the smooth version to the actual version. So just to recap, our main result is a polylog m seed length for the class of m-facet polytopes. The previous best seed length, if you do not assume anything on the facets of the polytope, had linear dependence on m. Equivalently, there's an explicit set of volume-preserving points of size n to the polylog m. The most obvious open problem is to improve on our 1 over epsilon dependence. Our log n dependence is optimal. It's not hard to show that you need at least log n dependence. It would be very nice to get polylog 1 over epsilon. And it's all very closely related to issues about convergence in central limit theorems. So it's very interesting for that reason. And there are other less concrete directions. Are there other complexity measures of polytopes? For example, if you give me a sphere, there's infinitely many facets, so our C length would be very bad, but a sphere is simple for some other reason. We're not, are there PRGs for other geometric sets other than polytopes? Can we give a PRG for all convex sets? Thanks.
So
as the base, and you mentioned the random set. Is there any work on like looking at what happens when you take like some other kind of randomness, like a random structured set?
That's basically what we're sort of doing, right? Limited randomness. Yeah.
So you mentioned the Littlewood-offord thing. You also need like a de-randomized version of that to
No, we don't. Yeah, it's sort of in the analysis. Yeah, it doesn't go into our PRG at all. It's like you give me any PRG that fools the smooth orthant modifier. Yeah, it sort of has nothing to do with randomness. Yeah, good question though. Although I think we can also de-randomize it for what it's worth.
Questions? Well, let's thank Liang again.